Black holes are one of the most mind-boggling aspects of space. For a start, they aren't actually objects. They are the result of the extreme warping of space-time. I'm Alex Milan, and you're watching Astrum, and in this video we will be exploring the unexplorable. Join me on this journey as we attempt to understand the weird science of how a black hole forms, what goes on around them, and explore what might actually allow for an escape from the most inescapable prisons in existence. Black holes come in a variety of sizes. The smallest observed black hole is around 3.8 solar masses. On the other side of the scale, we find black holes weighing billions of solar masses, so huge they would easily fit the entire solar system within the diameter of their event horizon. Black holes being created today are the final stage in the life cycles of particularly massive stars. When such a star is born, it is essentially balancing under the weight of two forces. The first is gravity pushing its mass towards its center. Down in the depths of the star, hydrogen atoms are crushed together with such force that they combine to form helium. This released energy is the second force. It radiates back out from the center of the star as heat and light, counteracting the force of gravity pushing in. In this state, the star will remain relatively stable until the reaction begins to stop as it runs out of its hydrogen fuel. If the star is massive enough, once the hydrogen begins to run low, the star will combine the newly formed helium into even denser materials like carbon, neon, and eventually oxygen and silicon. But then it begins fusing iron. The issue with iron is that it doesn't save any energy in its new form, so has no spare energy to release. Very quickly, the scale tips. The energy of this collapse is astounding, but the force is dependent on the original mass of the star. Like a hammer striking on an anvil, the mass of the star rushes down to meet the core with such force that the rebound of that blow is what we call a supernova. If the mass of the star and thus the force of the blow was too low, what remains is a neutron star, a small ball of matter at most around 25 kilometers in diameter, yet so densely packed with mass that it equals 1,000,000 Earths. But if the mass and thus force was big enough, physics as we know it breaks down and we are left with a black hole. When you see an image of a black hole, the black sphere you are looking at is not actually the black hole itself. Scientists theorize a black hole's true form is probably even smaller and denser than a neutron star. In fact, it is likely infinitely small and infinitely dense. A singularity. All objects with mass exert gravity. We've known this since the days of Newton. However, when Einstein came along in 1915 with his theory of general relativity, a contemporary of his called Karl Schwarzschild reasoned that there could exist objects so massive they could create enough gravity that light itself could not escape. When you look at a picture of a black hole, you are not seeing the black hole itself. You are seeing the event horizon around it. The demarcation line where gravity has become so powerful that light can no longer leave. Its effect on space is one thing, but black holes also impact time itself. According to Einstein, space and time are inseparably connected, and mass warps space-time. This produces an interesting phenomenon. To an outside observer watching matter fall into a black hole, as matter approaches the black hole, it will slow down until just before the event horizon, where it will stop altogether. You won't ever see it cross the event horizon. When first theorized, astronomers and physicists were uncertain if black holes were actually real. It was only 40 years later that the first evidence of a black hole was recorded. In 1964, using newly developed X-ray satellites, scientists noticed an object in the constellation Cygnus that seemed to be emitting a large amount of X-rays. In 1970, as telescopes advanced, they noticed that whatever Cygnus X1 was, it had formed a binary orbit with a star in its system, and this helped scientists calculate its mass. They discovered that this invisible object was 15 times more massive than the Sun. As the densest neutron star had an upper limit of 3 times the mass of the Sun, scientists realized this was most likely the first ever discovered black hole. Since then, we have discovered many black holes. This is how black holes can still be detected through X-rays. While black holes can't emit visible electromagnetic radiation themselves, the X-rays come from the accretion disks, where in falling matter gets heated to millions of degrees through intense friction. Black holes with no falling matter are basically invisible, with no bright accretion disk to spot. You may wonder if a black hole could ever stop being a black hole, or will it grow forever until there is no matter or radiation left in the universe. However, in 1974, in his paper entitled Black Hole Explosions, physicist Stephen Hawking postulated that there was actually a way that energy and thus mass could leave a black hole. But first, let me ask you a difficult question. What is nothing? Imagine a patch of space with nothing inside of it. No atoms of space dust, not even radiation passing through it, yet something fundamental exists here. We can tell when a beam of light travels through it. Light is actually waves of electrical and magnetic charge propagating forward in a straight line. A wave in the sea is energy moving through water. Similarly, a sound wave moves by passing energy between air particles. But in our vacuum of space, what exactly is waving? This hints at a fundamental something that exists even in nothing, a fabric that makes up all of reality itself. Quantum physicists call this something a quantum field. Scientists believe there are several quantum fields all overlapping each other and covering every single patch of the universe. One field might define all electrons in existence, while another may define quarks that make up atoms. Where nothing can be found, the quantum field is relatively quiet, like a guitar string that hasn't been strummed. But wherever mass or energy can be found, the quantum field is resonating. Due to Heisenberg's uncertainty principle, when we're looking at really tiny objects on the atomic scale, it becomes impossible to know too much about them. You cannot know both the location and direction of travel of an electron. When you apply this principle to quantum fields, particle and antiparticle pairs can actually pop in and out of existence as long as they only exist for a very short period of time. In an experiment done by Hendrik Casimir, evidence was found that this might actually happen. Casimir took two plates of conductive metal and placed them close together. This limited the number of virtual particles that could pop into existence between them, but all types could appear outside the plates. The larger pressure on the outside should push the plates together, and, in the test, this proved to be the case. Whenever a virtual particle appears, a second particle also pops into existence to pair up with it. While one is matter, the other is antimatter, keeping things overall at zero. These fluctuations in the quantum field quickly crash into each other and annihilate each other, removing them both from existence again. Black holes act a bit like putting your thumb on the guitar string of the universe. Due to their event horizons, certain resonances in the quantum fields are dampened down while others are not. Hawking imagined sketching a line through time in a patch of space where a black hole was born, stretching from before the existence of the black hole into the future after it. After the black hole had formed outside the event horizon, Hawking found resonances that perfectly matched the shape of thermal radiation flying away into space. As the black hole was creating this radiation, the black hole would have to pay the price. Every piece of Hawking radiation would coincide with an equal amount of energy lost from the black hole. This radiation would be colder than the background cosmic radiation and would have a wavelength as long as the black hole's event horizon itself. As some black holes have event horizons the size of solar systems, we have no way of detecting this kind of radiation. However, researchers at the Technion Israel Institute of Technology created a sonic black hole analog. After 97,000 experiments over 124 days, they detected multiple instances of Hawking radiation that matched Hawking's predictions. When you're walking on a beach and make a footprint in the sand, there's no question that it's your foot that caused the footprint. The order of causality is quite clear. But what if I told you that on the cosmological scale, the fundamental relationship between foot and footprint might be more blurred than you would intuitively think? Galilean relativity shows there's no difference between being completely still and moving at continuous speed. Right now, you are careening through space at 110,000 kilometers per hour due to Earth's movement around the Sun. Einstein took this further with his equivalence principle. There's no way to tell the difference between acceleration caused by gravity and acceleration caused by a rocket. Einstein realized that matter and energy cause a warping in the space around it, kind of like how a ball might bend the surface of a taut rubber sheet. In the words of physicist John Wheeler, space tells matter how to move, matter tells space how to curve. The most important thing about Hawking radiation is that it is non-local. It does not appear from the black hole itself, but from the area of space around it, up to billions of kilometers away. This hints at a universe where mass is simply a projection caused by space curvature. Are we simply projections, shadows on the wall of the universe being brought into life by something more fundamental going on in the curvature of space-time? Black holes might provide the answer to traveling faster than the speed of light and solving the energy crisis in ways we couldn't have even imagined until recently. There are only three things we can say about black holes with certainty. They have mass, they have charge, and they have angular momentum. Scientists can track objects that approach a black hole, and by seeing how quickly certain objects move, we can determine these fundamental properties that extend beyond the event horizon. I hope by the end of this video to have earned your like and subscription. Thank you for joining me on this journey into the weird science of black holes.